All right, so this is still solving differential equations day 2. This is model 2. All right, so we'll start with step number 1, which is to separate the variables. Right. Now keep in mind, you don't have to write out the words of the steps. I'm just doing that for notes and to reinforce the steps and hopefully to get you to memorize it a little bit quicker, but you don't have to be writing these words out by any means. Separate the variables. Okay, so we have an interesting situation over here. Okay, so we're going to cross multiply as we've done for all of the other questions. So dy equals e to the y plus x dx. Okay, so unlike model 1, we did not separate the variables automatically after cross multiplying. I still see that there's a y term over on the right side, and we really want to get all of the y terms on the left side. So back of this. The first do now that I gave you is going to be very important for a question like this. See, we're so used to sort of working in this direction. When you're given e to the m times e to the p, we understand that we have to add the exponents. But what we're going to be actually doing now is rewriting it not in the way that we're used to. See, currently in model 2, we have something that looks like this. And what we're going to do to the e to the y plus x is we're going to separate it. See, this really came from e to the y times e to the x. And it's not until you do that that you can truly separate the variables. See, now all we have to do is divide both sides by e to the y. I'm also going to further rewrite the left side. This is very similar to one of the questions that I did on Friday. I'm going to write this as e to the negative y dy equals e to the x dx. Okay? Now we've separated the variables. Now we're ready to go to step 2, which is to integrate both sides. Okay. No power rules in this question. We have 2 exponential functions with the base of e. So, we're going to review some of the same material that we did in the first model. Shoot this paper here. So we have to understand that when we find the derivative or the antiderivative of exponential functions with the base of e, that the antiderivatives, in this case, will appear to be nearly exactly the same. Right? And we did prove that in our recall example from Model 1, right? When we found the derivative of e to the 2x plus 1, we saw that the derivative also had e to the 2x plus 1, right? So it works both ways. What's not always consistent, though, is the coefficient, right, which we saw here. So at this point, you really shouldn't be comfortable that you have the correct antiderivative. What you really want to do is you want to do a little bit of a check, right? And really, 2 checks here, because we have 2 different e to the some exponent functions, right? So let's check the right side. If we have y equals e to the x, and we found the derivative in terms of x, it would be e to the x times ln of e times the derivative of our exponent, which in this case is 1. And sure enough, the derivative is e to the x. So as it turns out, the antiderivative that we have on the right side is sufficient. We just proved it here, and we did our quick little check. Now, on the left side, let's see how that works out, right? So we're going to find the derivative of e to the negative y in terms of y. So that's going to be e to the negative y times ln of e times the derivative of the exponent in terms of y. So that would be negative 1. So as it turns out, this one is off by a little bit, right? See, our derivative is currently negative 1 e to the negative y. And we really want the derivative to be positive 1 e to the negative y. So then you say, all right, well, my initial guess on the antiderivative was off. And how much was it off by? Well, I believe it was off by a factor of negative 1, right? You want to think to yourself, what factor can I multiply this by to achieve what it's supposed to be? And negative 1 times another negative 1 would give you positive 1, which is exactly what we want. And that would be an indicator of how much you're off in your original, educated guess of what the antiderivative is. Okay. So we're ready for step 3, which is to find the c value. So we have an initial condition. This is our x, and this is our y value. Right? So we have negative 1e to the negative ln of 4, right? Because there's already a negative in the exponent, and the y value itself is also negative, equals e to the 0 plus c. All right, e to the 0 is not 0, it's 1, be careful. Okay, and then we have negative 1e to the ln of 4. And this is a really, really, really nice shortcut. You know, the exponential function and the natural log function are inverses. And this would not be a calculator question. And this simplifies very, very well. Whenever you have an e to the ln situation, essentially think about them as sort of crossing each other out. Kind of like if I had the square root of 4 squared, right? The square function and the square root function are inverses of each other. So in a situation like this, we would say, they cancel each other out. We would be left with 4. So it's very, very, very similar. These are inverse functions. So really, this simplifies to be 4. In fact, negative 4. Because it's multiplied times negative 1. That's a very helpful simplifying trick. We'll subtract the 1 over, and we get negative 5. So our c value is negative 5. Okay. All right, so step 4 is to isolate y. Okay, so we have negative 1e to the negative y equals e to the x. And our c value is negative 5. Okay. We are solving for y, which is in the exponent, so logarithms should be coming into your mind. But first and foremost, we want to get rid of that coefficient of negative 1. So I'm going to multiply everything by negative 1. So that's going to be e to the negative y equals... you know what, I guess I'm going to rearrange this. 5 minus e to the x. Just makes it look nicer for me. Okay. And then I am going to natural log both sides. Okay, parentheses, very important on the right side. So I have ln of e bring down the negative y. And ln of e is 1. So then I just have to either divide both sides by -1 or multiply both sides by -1. Now, multiplying the ln of 5 minus e to the x by -1 just makes the coefficient of the natural log -1. You're not actually multiplying the 5 and the negative e to the x times -1. Okay. And then step 5 is we do have to check our initial condition, which was y of 0 equals negative ln of 4, right? So this is our x, this is our y value. All right, so we have negative ln of 4 equals -1 times ln of 5 minus e to 0. So we have negative ln of 4 equals -1 times ln, well, e to the 0 is 1, 5 minus 1 is 4. So it looks like we have a valid statement, right? So at this point we can go back, circle this as our final answer, and there you have it.